Have you ever wondered how the world's most powerful artificial intelligence systems actually figure out how to beat us at our own games? Right? It's really easy to assume it's just raw, calculating brain power. But the truth is actually way stranger, and honestly, a lot more fun. To understand how modern AI can conquer problems with literally almost infinite possibilities, we've got to trace its roots back to a pretty surprising place: the roulette wheels of a casino. Welcome to The Explainer. Today, we're taking a really fascinating journey into the math of randomness. We're going to dive deep into the Monte Carlo game model and see exactly how rolling the virtual dice became the absolute secret weapon for machine learning, complex problem solving, and superhuman game design. Okay, let's dive right into this. Here is our roadmap for today. First, the casino connection. Then, the Monte Carlo method. Next, navigating the game tree. After that, conquering complex games. And finally, real-world decision-making. So part 1, the casino connection. Let's look at the 1940s origins. The origin story of this incredibly complex mathematical tool actually starts back in the 1940s, right in the middle of one of the most secretive scientific endeavors in human history. The year is 1946. You have these brilliant mathematicians, Stanislaw Ulam and John von Neumann, working on the Manhattan Project. They're trying to figure out the probability distribution of energy released when a neutron collides with an atomic nucleus. Talk about high stakes, right? But the problem was just way too complex for pure mathematical analysis at the time. Then, Ulam has this absolute epiphany. Instead of blindly trying to calculate every single possibility, why not just create a massive data set by simulating random inputs and just seeing what happens? A colleague actually pointed out that this random selection of variables was a whole lot like the randomness of a roulette wheel. And get this, because Ulam's uncle frequently borrowed money to go gamble at the famous Monte Carlo casino in Monaco, they decided to name this brand new statistical modeling technique the Monte Carlo method. Moving on to part 2, the Monte Carlo method. This is all about going from chaos to certainty. So the crucial point here is that at its core, the Monte Carlo method is a deterministic process. It utilizes random sampling and multiple simulations to basically estimate unknown quantities. Think of it like this. If you have a system that's just way too complex for traditional analytical solutions, you inject some randomness, you set up your constraints, and then you run a simulation. But you don't just run it once or twice, you run it hundreds, maybe thousands of times. Now, individually, each of those random results tells you almost nothing. But collectively, all those random trials start to build up a highly predictable probability distribution. You're essentially using sheer statistical volume to map out the most likely reality. Which brings us to part 3, navigating the game tree. Let's see how this leaps into AI. Now we're going to look at how this mathematical concept jumped straight from physics over to the world of game theory and artificial intelligence. This was really championed by researchers like Bruce Abramson back in 1987. For a long time, AI relied on deterministic models, like the minimax algorithm. Minimax basically tries to evaluate every single exhaustive possibility on a game board. And hey, that works great for a game like chess. But older AI hit a massive wall with games that suffered from what we call the curse of dimensionality, games with a huge branching factor and super deep search trees, where the number of possible moves is literally greater than the number of atoms in the universe. That is exactly where Monte Carlo tree search, or MCTS, steps in. Instead of trying to calculate everything, MCTS is probabilistic. It randomly samples paths to estimate the true value of an action, completely bypassing the need to map out the entire universe of possibilities. What's really interesting about how this works is that the algorithm builds an asymmetrical search tree. It doesn't grow evenly in all directions. Instead, it's constantly balancing two things: exploration and exploitation. Exploration means looking into new areas of the game that haven't been sampled very well yet. Exploitation, on the other hand, means focusing heavily on the specific branches that already look like they're the most promising, based on those earlier random tests. It's incredibly smart. And this whole search tree practically functions like a continuous 4-step engine. First step is selection. The algorithm starts at the root and picks the optimal path down to the end of a branch, known as a leaf node. Second is expansion, where it simply adds a new child node to that leaf. Third is simulation, and honestly, this is where the real magic happens. It plays the game out from that exact point to the very end. And finally, backpropagation. It takes the final result of that simulation and updates the statistics of all the nodes it just passed through. Then it just repeats this loop over and over again. That simulation step is often called a playout or a rollout, and it is utterly fascinating. The AI essentially plays a simulated game against itself using completely random moves all the way to a terminal state. By terminal state, I just mean the very end of the game. The craziest part, it doesn't even need to know intermediate strategies. It only needs to know one thing. Was the final result a win, a loss, or a draw? By recording those final states, the algorithm continuously updates its own internal statistics, gradually biasing its future choices heavily toward the paths that most frequently led to a win. And listen, we aren't just talking about a few practice rounds here. We are talking about thousands upon thousands of simulations. Whether it's a board game developer trying to balance a brand new deck of cards or an AI trying to determine its absolute best next move, these algorithms can run over 1,000 random playouts in a fraction of a second. It's mind-blowing. That sheer astronomical volume of random testing is exactly what turns chaos into sharply focused foresight. Let's move on to part 4, conquering complex games. This is really AI's ultimate testbed. Games have always offered a really rich, measurable way to test AI research, and Monte Carlo tree search has systematically dismantled some of our greatest human challenges. The evolution here is just remarkable. Back in 1987, Abramson proved that random sampling could actually approximate the value of moves in simple games like tic-tac-toe. Fast forward to the 2000s, and variations of MCTS were hitting world champion levels in Scrabble and backgammon. But the true watershed moment? That arrived in 2016. That's when Google DeepMind's AlphaGo famously defeated the human world champion Lisa Dole at the game of Go. Go has a notoriously massive branching factor that had stumped traditional AI for decades. But by integrating MCTS with neural networks, the AI finally navigated the impossible complexity of that board.
And the versatility of this method is just staggering. MCTS isn't just locked into classic perfect information board games. Not at all. It's been successfully adapted for real-time strategy games, like Miss Pac-Man and StarCraft, by using clever approximations to handle tight time limits. It powers high-level campaign AI and turn-based games, like Total War Rome 2. It even tackles incomplete information games, like poker. It actually groups different game states into buckets so it can find approximate winning strategies without even knowing the opponent's cards. How wild is that?
Which brings us to our final section, Part 5, Real-World Decision-Making, taking this from the board to human crises. But here's the thing. AI learning to beat us at games is really only half the story. Because if you can mathematically model a board game, you can model a human crisis. So how do researchers actually go about modeling a real-world crisis? They use a framework called the Monte Carlo game model, or Monte Carlo game theory. It brilliantly takes messy, complicated human problems where you don't have perfect quantitative data and maps them into a series of deterministic strategic games. Then it simulates the outcomes thousands of times to figure out the probabilities of different equilibria. This is absolutely vital for what researchers call multi-criteria decision-making. Just think about major resource management conflicts where you have multiple stakeholders with totally conflicting interests. Traditional decision-making models almost always assume perfect cooperation, which, let's be real, rarely ever happens in reality. The Monte Carlo game theory approach actually accounts for non-cooperative behavior. It doesn't just sit there and prescribe some perfect utopian solution. Instead, it actively predicts the most likely outcomes, based on the very real fact that human beings will often act in their own self-interest when things get uncertain. To put that into perspective, this precise Monte Carlo game model was applied to the massive water management conflicts in California's Sacramento-San Joaquin Delta. By mapping out the fiercely competing interests of farmers, environmental groups, and urban centers as a strategic game, and then running those probabilistic simulations, researchers were able to identify what they call non-dominated alternatives, basically, the best possible compromises. They could predict the most likely policy outcomes without needing every single party to agree on one aggregated objective. It completely takes the subjective guesswork out of complex, high-stakes resource allocation. From a mathematician's gamble in a Monaco casino to mastering the ancient complex game of Go to actually allocating vital water resources in a modern conflict, the journey of the Monte Carlo method is just an incredible testament to the power of structured randomness. By fully embracing chaos and simulating it at an absolutely massive scale, we've unlocked a way to see right through the fog of almost infinite possibilities. And it leaves us with a truly exciting question. If an algorithm can conquer the world's most complex games just by rolling the virtual dice, what impossible human problem is it going to solve next? Thank you so much for joining me on The Explainer. Keep exploring, keep questioning, and we'll see you next time.